This is Dr. Carroll, and this video is about minimum spanning tree exercises. Let's jump in. So if we had a tree with, if we started with a graph, with edges AB, AF, AG, BC, BG, CD, CG, DE, DG, EF, EG, FG, then how would we produce a spanning tree? And particularly, I want to focus in on a depth-first search spanning tree and a breadth-first search spanning tree, starting at vertex A. So I've graphed that here. These same edges are represented here. And so if we did a depth-first search, we're going to get a tree that looks like that. Is that a tree? Yes, there's no cycles. Every vertex is connected. There we go. That's our depth first search spanning tree. Starting over, going back to the original, if we did a breadth first search tree, we'd include AB, AF, AG, and then we'd branch out from there, BC, EF, and then DG. And so we'd get a different spanning tree. So part of what I wanted to illustrate with this is there are many different spanning trees that could be produced. Shown textually here, the different spanning trees. Let's do another graph. So if we start with this graph with edges AB, AD, AF, BC, BG, CD, DE, EF, and FG, a depth first search is again just going to go alphabetically and go through that, and so we have a tree here. Looks kind of more like a vine, but it is a tree. And then if we were to do a breadth first search, we'd go by levels from A, and then everything adjacent to those vertices, and would produce a spanning tree that would look like this if we favored if we always chose the lowest letter first. There we go. We've produced some spanning trees. Now let's utilize not only spanning trees, but move into moving spanning trees. So let's interpret the vertices for the graph as cities, and then the edges as the cost to produce some networks, for example, a fiber optic cable. And so what is the lowest cost to connect every city starting at A to the graph? And then make sure we draw all the edges that are part of the solution. So starting with a graph with weights AB with a weight of 8, AB with a weight of 9, AF with a weight of 8, AG with a weight of 5, BC with a weight of 2, BG with a weight of 3, CD with a weight of 7, CG with a weight of 4, DE with a weight of 2, DG with a weight of 1, EF with a weight of 5, EG with a weight of 6, and FG with a weight of 7. That would look like this. Okay, our first graph, but with weights. We have two options, Prims and Kruskals. Let's remind ourselves that with Prims, we're going to iteratively add the lowest cost edge that adds a vertex that's not already in our minimum spanning tree. So starting here, we're going to start off by adding in A, because that's our designated starting point. And then we're going to add in the lowest cost edge that expands our minimum spanning tree. Well, our minimum spanning tree is just A right now. So we would include the edges A to B, A to F, and A to G, and would take note of their weights. And so we notice that the edge from A to G is the minimum, and so we would include that in the minimum spanning tree. Here, blue is shown as the minimum spanning tree is shown here in blue. Then now we need to update the weights that we're evaluating to find the lowest one. So then we'd include all of the edges from G because we've expanded our tree. So now we have many more edges, all of the edges from G to all the other vertices. So now we look through all of the gray edges, all of the edges that go from our minimum spanning tree to a vertex that's not in our minimum spanning tree, and we find the lowest one, and the lowest one is 1, and so we would include the vertex D, and then we would update to include the edges that go from D. Again, we'd look at all of the edges that come from the minimum spanning tree that go to a vertex that's not the minimum spanning tree, and we would choose an edge with length 2 from D to E. Notice we don't consider the edge from B to C because neither B nor C is part of the minimum spanning tree yet. We also included the edge from E in our weights, and now we go through all the edges that start at the minimum spanning tree and branch out to a vertex that's not in the minimum spanning tree. And so we would include the edge with weight 3, including B. And now we have included the edge from B to C, and now that is the lowest cost one. And so now we're going to include C. Now we're going to look at all the edges that include a new vertex, and there's only one left, that's F. And so the least expensive way to get to F is through E with a weight of 5. Shown textually, we're going to add A, and then G, and then D, and then E, and then B, and then C, and then F. And that's going to give us a total cost of all of the weights is going to be 18. And there's no way to get any lower. And so 18 is the minimum cost to connect all of those vertices. Now let's see that played out with Kruskals. Starting over again. Now with Kruskals, we take starting over again, we start with our original graph. Now remember, with Kruskals, we're going to add the lowest cost edge that connects a previously unconnected component. So we're going to start out by making all of the vertices their own set. So we could call these forests. We're going to make a whole bunch of trees and connect them together in a greedy fashion. So now notice we're not starting with A necessarily with this one. Now what we want to do is look at two sets and find the lowest cost edge that joins two sets together that were not previously joined together. And so that edge is a weight of 1, and so we're going to add that in here. And so now D and G are in the same set. They form a tree. And then we apply this again. What is the lowest weight that joins two vertices that weren't previously in the same set? And we're going to have BC with 2 here. We're going to apply this again. We're going to find there's another edge with weight 2, and that's DE. And so now we've added an E into the set with D and G. We're going to apply this again, and we're going to use the edge with weight 3, and now we have a larger tree, and then we have A and F still. We're going to now, one way to do this is take all the edges, sort their weights, and go through them. And so at this point we'd get to edge weight 4 and would say, oh nope, that C to G, they're already in the same set, so we're not going to include them. So we would skip that. The next weight is 5, and so we would include A to G and put all of those in the same tree. And there's another edge with weight 5, and so that would connect F in, and then we have all vertices connected. And so then here we have our minimum spanning tree using Kruskal's algorithm and how it built it up. And so we would, shown textually here, we're going to start with each vertice in its own set. We're going to take all of the edges and sort them by weight. And then we're going to go through top to bottom and decide, do we include it or not. DG does combine two previously uncombined sets, D and G. And so our forest of trees over here, we have one less tree because we combined D and G. We'll look at the next edge, and yes, we included that one, and now we have a smaller forest. And then we look at the next edge, weight 2 again, and we have we've combined another set because of the edge from D to E, B to G. We've further combined sets, and as I mentioned, the weight 4, C to G, C and G are already in the same set, so there's nothing more to be gained by doing that, so we skip that one. But A to G does connect to previously unconnected sets, and then E to F, and then we're done. Let's look at another graph here. And so this graph has A to B with a weight of 2, A to C with a weight of 5, A to F with a weight of 2, B to G with a weight of 3, B to H with a weight of 4, C to E with a weight of 6, D to E with a weight of 8, D to F with a weight of 6, D to G with a weight of 1, E to F with a weight of 5, G to H with a weight of 2. Now let's apply Prim's algorithm on this one again. And Prim's algorithm, we're going to arbitrarily start with A, because that was what was specified in the prom definition. And again, we're going to look at what edges to include. And so we're going to highlight those in gray to illustrate all of the edges from A are under consideration. We're going to choose the lowest cost one. And I'm going to favor the alpha lower on the alphabet here. So our minimum spanning tree has grown by 1, and it will every iteration. So our minimum spanning tree includes A and B. And then we need to include the edges that are adjacent to B to be considered. And then the next edge we include is F. And then we can see now the vertices adjacent to F. And now we're looking at all the gray edges, and we see that there is a weight of 1. Notice we do not yet see the edge with weight 1 yet from D to G. And so we include the edge from B to G. Now we can see that edge, and so then we'll choose that now, be the lowest cost edge, and expand further. And now we're looking at all the edges that connect a new vertex. And so there's an edge with weight 2 for H. We're going to connect there. And then we're going to connect edge weight 5, A to C. And then there's one more edge weight 5 to E. And there we go. We now have a tree. There are no cycles if you only consider the blue lines here. And it is of a minimum weight. We can see this textually here going through, adding in the edges, adding in the vertices and the corresponding edges. Now let's talk about Kruskals. So same graph going through, we're going to make all of the vertices their own set. And now we're going to look at what's the edge that has the lowest weight and then combine that set. Then we're going to look for the next lowest edge weight, and we're going to combine them into a set, and we'll apply that again. And so then we'll combine, we'll reach out. So now we've taken care of all of the edges with a weight of 1, all of the edges with a weight of 2. Now we're on edges with a weight of 3. Now we're on edges with a weight of 4, but we notice, oh, B and H are already in the same set, so we're not going to include that in our minimum spanning tree. Now we're at 5 and 5, and then we're done. So we have our set, we have all of the edges sorted by weight, and yes, the first time through we're obviously going to connect it, and so we've connected those sets together. And then our edge of weight 2, we're going to include that in our minimum spanning tree as well. Edge of weight 2, again, yes. 2, yes, that combines new components. 3, yes. 4, no, we're going to skip that one. But edge of weight 5, we are going to include that. And then we have one more vertex to include, and we got it with our next one with weight 5. Great. Now the last question. Given a graph G with vertices V and edges E, with an adjacency matrix representation, what is the runtime to calculate a minimum spanning tree? And let's also consider adjacency list while we're at it. So there's a couple of different ways to think about this. If we took a naive way of searching over all edges for each vertex, then we're going to end up with adjacency list and adjacency matrix giving us slightly different values. Adjacency list, we're going to have the size of the vertex times the size of the edges if we're doing this over and over and over again. Whereas adjacency matrix, we're going to end up needing V squared to find all of those low cost edges. We could do something better though. We could use a priority queue, a binary min heap, for example, and then if we store the edges in a binary min heap and then remove one and update the minimum distance to our growing minimum spanning tree, then we can get that down to big O of E times log of V. But that's not all. We can do even better. If we're using prims and we're employing Fibonacci heaps, we can get that down a little bit lower to E plus V times log of V. Thank you for watching. Check out my other videos too.